Welcome back. We are discussing about water treatment, and in this video we'll be talking about the plane sedimentation aspects of water treatment. And what you see here is the sedimentation means it is nothing but settling of particles by simple gravity. There are two types of particles: inorganic having a specific gravity 2.5 to 2.7, and organic particles have a specific gravity between 1 to 1.2. There are two types of settling. One is called discrete settling, is also called as type 1 settling. Another one is called flocculent settling, is also called as type 2 settling. But the plane sedimentation, we'll be mainly talking about discrete particle settling. What is the meaning of discrete settling here? The size and shape of the particles does not change with depth. And usually, if you assume a specific spherical particle, and when it is entering into the liquid there, at the having some diameter d and the area a, and by the time when it is settling to the bottom, the same diameter is assumed to be existing and without the changing of any surface area. That sort of particle is called as a discrete settling. Flocculent settling means the size and shape will be changing while it's journey through to the bottom. This type of particles we'll be discussing more in coagulation part. The plane sedimentation, we mainly talk about discrete settling. Whenever we talk about settling of particles, then what are the forces acting on it, we should again concentrate. If we assume that a spherical discrete particle of diameter d and surface area A is there in a tank which is under the process of settling, it will be influenced by one gravity force by the weight acting downward direction and the buoyancy force in the opposite direction, upward direction. And because if the particle is moving in a fluid in a downward direction, a drag will be there in the upward direction. So one gravity force in downward direction and then drag and buoyancy in the upward directions. These two are balanced. If you write this equation and then balance with the drag is equal to Fg minus Fp, and you write down the conventional equations here for drag force is equal to half CD A rho W into V is nothing but settling velocity of the particle. And here density is nothing but volume into density multiplied by acceleration due to gravity. And buoyancy is nothing but volume of the particle having displaced volume of water, that is the density of water. And when you're writing here, A is equal to pi by 4d square. The settling velocity is now 4g into rho p minus rho wd by 3 cd rho w. So this is a generalized settling velocity equation. Depending on the nature of the flow in the tank, we are going to change this equation into subsequent forms. Coefficient of drag depends on the Reynolds number. If you assume a laminar flow, the CD is equal to 24 by RE, where RE is the Reynolds number. You're writing as a rho W V D by mu. Rho W is nothing but the density of the fluid, water. V is the velocity of the particle. D is the diameter. Mu is the absolute viscosity. And if the flow is not laminar, transitional, the CD is having some additional terms, 0.34 and 3 by root RE for the CD value. If you substitute the CD is equal to 24 by RE, what we are going to get is two forms, 1 by 18 mu GD square rho P minus rho W. And if you put the kinematic viscosity in place of absolute viscosity, we are going to get 1 by 18 GD square by mu Sp minus 1, where Sp is nothing but specific gravity of the particle, and the denominator is nothing but the kinematic viscosity. So this is called as Stokes' law, which is an important derivation in the sedimentation analysis. And this is valid for particle size less than 0.1 mm, laminar flow, and Reynolds number less than 1. And a conventional form of the Stokes' law with respect to time, with respect to temperature, can be identified. as V is equal to 418 Sp minus Sf d square 3T plus 70 by 100. T is the temperature of the fluid in centigrade. Sf is nothing but specific gravity of the fluid. Usually we take water, so Sf is equal to 1. So it becomes 418 Sp minus 1 d square 3T plus 70 by 100. And this is applicable for temperatures more than 10 centigrade. Now let us see the settling analysis part. So let us assume a tank you are considering so that a raw water flow of Q is now entering and leaving in a tank of dimensions length L, B, width of the tank B, and water depth H. So that volume of the tank is nothing but LBH. When the particle is entering here, a fluid particle, it will undergo two different velocities. One velocity will be in horizontal direction so that the particle moves in horizontal direction. Because this particle is having some density, so it will also settle down with some settling velocity as discussed just now in the previous section. So now there are two vectors here, and then the particle will be moving as a resultant of these two vectors and goes directly to the bottom of the tank in the diagonal direction. So what's the most important thing here is by the time the particle travels in the horizontal direction till it reaches the end, it takes a time th. Th stands for the time of horizontal travel. And the same time, the particle is also undergoing a time of travel in the vertical direction, dv, which is corresponding to the settling velocity and the depth of the tank. So for 100% settling of all these particles, the time of horizontal settling, so time of horizontal travel must be same as the time of vertical travel. So using this relationship, we are going to identify. When you take these two times, then only the particle without settling in the tank, it goes out otherwise. So when the time of settling is same, all the particles will be removed here. So now from the relationship here, from the geometry of the section, horizontal velocity VH is equal to Q discharge divided by area perpendicular to that, B into H. So is equal to L by TH. Okay, that is nothing but horizontal time. So Vs is equal to Q discharge divided by area perpendicular. So area Vs is perpendicular to the surface area. So VH is perpendicular to the cross-sectional area. So 100% settling, time of horizontal travel must be equal to time of vertical travel. So L by VH is equals to H by Vs. So 100% settling, we also have another relationship here. Settling velocity is equal to ideal settling velocity, which we are defining as surface overflow rate, V naught. So what is exactly is happening here? So surface overflow rate now can be equated to your Stokes law as 418 d square SS minus 1 3t plus 70 by 100. So what is Vs here? Vs is nothing but Q by LB, nothing but Q by surface area. So ultimately what we are saying is surface overflow rate is nothing but discharge divided by surface area. So the settling of the particle finally depends on the surface area but not on the depth. Now what about the settling efficiency of the particles? Now we will try to consider the same situation. The diagonal here having an ideal velocity of V naught, and we'll consider two velocities here, V1 and V2, one above the diagonal and one below the diagonal. So here from the Stokes law, what we say, Vs is proportional to d square, forgetting about all other terms. So when Vs is more, d square also will be more. So then what will happen when Vs is more, d square is more particles are going to settle down to the bottom. And when Vs is less, that means d square is also less compared to the ideal velocity. So some particles will be there under suspension. How you are going to find out that? The settling removal efficiency of these particles, we take as a ratio of the velocity of that particular particle, settling velocity of that particle, with respect to SOR, which is nothing but ideal settling velocity. Based on that, we will be deciding how much percentage of particles are settled down. For example, if I take SOR as 20 meters per day, V1 is equal to 15 meters per day, V2 is equal to 25 meters per day. That means this is nothing but these particles are having a settling velocity as 15 meters per day. These particles are also having a settling velocity of 25 meters per day. So now if for the first one, if I look at here, the ratio of the settling velocities here, V1 divided by V naught, 15 by 20, so less than 100, so 75%. Only 75% of the particles are removed with this settling velocity. Now what else you see here? V2 is equal to 25, V naught is equal to 20. So ratio you can take more than 100. So all particles are removed. So this is how we are going to come into a conclusion. What else is also to be understood is all the particles which are corresponding to a settling velocity of SOR of V naught, suppose is called D naught. If the particles are having a size greater than or equal to that particular D naught, they'll also have a higher settling velocity. So they will also be removed. Other way to understand the settling analysis. If we are finding out a particle which is having a size less than, which corresponds to that of SOR, that will be removed partially. Now we have another term called score velocity or displacement velocity. What is the meaning of this displacement velocity? Here we are having a sedimentation tank, and the water is now entering with some horizontal velocity like this. The horizontal velocity like this, and some all the particles are settled down to the bottom. So they are already settled down. If the velocity is VH is smaller, then automatically all the water will go without any disturbance to the particles settle down. If the velocity of the horizontal velocity of this water is more, then ultimately it's going to create some disturbance to the settling particles. So these settling particles will try to rise into the water, with some velocity called the displacement velocity or score velocity, VD. So this velocity VD depends on a number of fundamental aspects of fluid mechanics. Our main job of sedimentation is all the particles should settle, they should not rise. So what the condition is, VH should always be less than VD. So condition says VH should always be less than VH so that the settled particles are not disturbed and not rising. So the factors corresponding to the rise of settled particles, they're identified, and then we are having an empirical equation based on that fundamental fluid properties of this material. Vd is equal to 8 beta g by f into sp minus 1 into d, where d is the diameter of the particle. We are writing in terms of centimeters, and this should be in centimeters here. And the sp is nothing but the specific gravity of the particles, and the g is the acceleration due to gravity in CGS units, and the f is the frictional factor. Beta is again another factor here, 0.04 for unigranular sands and greater than 0.06 for non-uniform sticky materials. And the F is coming out to be a Darcy-Weishbach factor, which is 0.025 to 0.03. So using this equation, we can calculate VD, and when you're going for design of sedimentation tanks, so what we have to do is we have to go for a check that horizontal velocity applied in the tank should be less than that of displacement velocity.